Hello, everybody. Today in our Engineering 101 podcast, we have a very intriguing subject, if I say so myself, because it's something that we always thought about, but really never really knew that there was a real understanding for it. So, hi, Wolfgang. How are you?
Very well. How are you doing?
I'm good.
It's nice and warm outside.
Yeah, the weather is very nice, actually. It's somewhat it's a Hamburg summer, to say the least.
It's Hamburg summer.
It's Hamburg summer, yeah. So my question today is, every time when you think about, like, let's say 15 degrees in terms of temperature, okay? Yeah. When you say 15 degrees water, it feels very cold. Oh my God, the water is 15 degrees. How am I going to jump inside? It's not possible. But when you say 15 degrees, the temperature around, oh, it's spring, it's very nice. And then you always think, how is there a difference between 15 degrees in air and 15 degrees in the water? Why is it different?
Because when you feel cold, your body loses heat. Mm-hmm. Heat is transferred into the medium around you. Okay. And water takes up the water very quickly, but if you have another fluid, which is air, mm-hmm. that doesn't take up the heat so quick. Understand that? We have to look at the thermal conductivity of the material. Okay. And we have a device that explains it. Uh-huh. In this cylinder, we have two parts, uh-huh. an inner part and a very thin layer of fluid, either gas or air, uh-huh. To show the heat transfer through this fluid. Okay. And we can make a very nice experiment to show that to you, uh-huh. how your sweater insulates or how the air insulates you so that you're not freezing. But if you jump in the cold water, you get chilly. Okay. Okay. In this experiment, we want to demonstrate the heat conductivity of a fluid which is in the small layer between this inner cylinder and the outer cylinder. For that, we can heat the inner cylinder and we can monitor the temperature inside. And we can cool the outer cylinder with cooling water and monitor the temperature of the cooling water. We can control the heat energy brought into the cylinder, and we measure the flow of water through the cooling jacket. Mm-hmm. And so we know the amount of heat being transferred through our fluid. Okay. And for that we have a graphic display, mm-hmm. how that experiment evolves. It's automatically controlled by the computer. Mm-hmm. It's very easy to operate. Yeah. And it shows us how good our fluid conducts the heat. Basic principle of fluid dynamics from the inner cylinder to the outer cylinder. Okay, so to speed up the liquid. Can show us, and that's what you experienced. Temperature change according to different fluids? Correct, yeah. Okay. So you either can use gas, air, or other gases, or you can use liquids like water. Yeah, okay. Ethanol, whatever you want. Okay, very interesting. What is shown in the graph here? What does the graph exactly show us? The temperature development. That means we have the inner temperature, the outer temperature, and the heat conductivity, the lambda. So how many watts per meter and Kelvin are transferred? Oh, okay. So the amount of energy, the temperature difference, and the surface. Okay. And for this one right now, is it gas or is it... In this case, it's gas. We have trapped air. We have brought air in. Okay. Very interesting. So we can show how much air you have to cover around you not to get chilly in winter when you have your 37 degrees body temperature, yeah. and you want to go outside into a cold environment. Uh-huh. How much insulation do you need not to get chilly? Okay, so that's, for an example, that's what they use to, let's say, something that's not like, I don't know, it has to do with engineering much or not,
what they do, the jacket, the isolation jackets for winter.
Yeah, we do not calculate the jacket, but we
Yeah,
calculate the rate of
trap
heat
of
transfer.
yeah.
And that is used in many applications.
Okay.
Of course, for textile engineering as well as for construction engineering, how to install the insulation
Same
layers.
like the insulation at homes to keep the
Correct,
homes warm in
yes.
winter. Okay. It's very nice. That's because our bodies have its own temperature. That's why it feels different.
The water
Has its own...
conducts the heat better than the air.
Yeah.
So it takes away the heat from your body that makes you chilly.
Ah, okay. So
all temperature loss makes you feel chilly.
Okay, because it's the water has more like direct contact with your body than
the gas, the air also has the direct contact.
Yeah, but it doesn't get you wet.
The gas doesn't conduct the heat, so it stays.
Yes.
Only if the gas is changing, if you are standing in front of a fan, you're getting cold as well, because we always bring in fresh cold gas. And then that is called convection, not conductivity.
Okay, that's very nice.
It's a different type of heat transfer.
Okay, that's actually very interesting information.
And that is the reason why we have such a thin layer to avoid convection, only to make sure that we only have conduction.
It's kind of showing what happens in real life with the thin air layer It's not heavy, so it's as close as it can be
to the nature. Yeah.
Okay. That's very nice. And if I have a question. This light blue line, like in this turquoise, this baby blue, the one on top.
This one here, that is our heat transfer rate. Do you see the temperature rising? Let's two, but then we see the temperature rising, the internal temperature rising. And we have the jacket temperature still constant, because there is no conductivity.
Yeah, okay, so it's completely kind of separated from...
Yeah.
Okay.
So now we see the temperature and the calculations of the lambda and the delta developing.
Okay. That is very, very interesting, honestly. Because it's something that I am sure everybody has thought about. Why is the water... Why if you drink 15 degrees water, you say, oh my God, that's very cold water. But if it's 15 degrees, it's spring. So it's always something that I'm sure everybody has thought about before.
Yeah.
And
it's in winter, how much clothes do I have to put on?
Yeah, and also 15 degrees in winter is completely different than 15 degrees in summer.
That is this mixture of conductivity and convection.
Yeah.
Particularly when the air has a certain amount of humidity.
Yeah.
You have a different convection rate, heat convection rate because of the humidity.
Yeah, and all these things like you see here close up, the device is just really small. And you would not think that this device can give you that output. It's very interesting.
This is such an important part in thermal physics, and it's so easy to do. Yeah. But in this case, less is more.
Yeah.
The less volume we have, the better results we get.
Yeah, okay. Now it makes more sense.
So and that is the delta between TU incoming temperature and outgoing temperature.
Okay.
That is coming from the bottom.
That is very nice.
But here we see the development of the temperature.
How it's rising slowly.
Outside.
Surely, yeah.
And this is our heat conductivity.
Yeah, when we add
So the higher the delta is, the more we conduct, and the lower the delta. So and here the delta is getting higher between inner temperature and outer temperature. Conductivity goes a little bit down.
So the heat is getting very close to the delta as it goes up. Very nice. That's very interesting. I don't think it's something literally that has been going through my mind for a very long time, but I never really, let's say, I never really got the logic behind it, because I'm like, how's that possible? Maybe it's the sun, maybe, and then like making scenarios, but I never really, it's sounds very complex when you think about it, but it's it's much simpler than people could think. And I think that's the reason why we are doing this podcast, is to make people realize that actually engineering is life, is everything we are doing every single day. And that's the best part, like that we are.
And particularly this topic makes people think since generations.
Yes.
And it started with the ancient people who started knitting the wool from the sheep and making their clothes. And they were thinking about it, how do I keep myself warm? And how do I make it that I'm not sweating in summer?
Yeah, okay.
So, and thermal engineering has to encounter a lot of factor.
Yeah.
Heat conductivity like this, heat convection, and radiation, because your body also radiates heat.
Yes.
Like the sun.
Yeah.
And we have to keep this temperature, all these levels aligned, that we are not getting cold and that we are not overheating in summer. So for that, sweating, evaporation is a big factor. The last few days it was very humid, so we were almost not able to sweat. So we all felt very hot.
Yeah, and not just hot, and it was also like it's like there's no air in the you could not breathe properly. The air was very dense, so there was no air. Yeah, it's very interesting.
So there was a very high temperature. Your body wanted to get rid of the heat. So he wanted to radiate, but there was all the other radiation from the outside temperature, from the sun and the buildings. And there was so much humidity that there was no evaporation. So you could not sweat. There was no convection, as there was no wind.
Yeah. So there was nothing that would trigger the body to sweat. So there was no change in temperature. It was just
all these rules make the engineers over the generations think how to get comfortable. That makes it thinking about the ideal way of clothing. That makes it about thinking about the ideal ambient temperature, humidity conditions in a good living environment.
Yeah.
This is all.
And that's why also houses in Germany are much warmer, because they have very big isolation for temperature.
Yeah.
So they keep the temperature inside. And that's why summer here feels much hotter than summer anywhere else, even though the temperatures are not necessarily that high, but the humidity and the fact that the buildings are capturing the temperature, it feels much warmer, right?
Yeah. That is the challenge for the engineers. Building a building which keeps the warmth in winter and doesn't let the heat in summer.
Okay.
And then it comes back to heat conduction and heat convection. And of course, storing of the heat in the building materials. And also the heat storage follows the rules of conduction and convection. Because every material has its specific heat capacity. So water has a very high specific heat capacity, but we can't live in water in houses made of water.
Yeah, exactly.
We are no fish.
Yeah, exactly.
So we have to use rocks or wood or things like that
to imitate what's the way the air is.
Yeah.
Okay. So, yeah, that's why, for an example, in countries that are usually very warm in summer, their houses are not isolated enough in winter, so they feel the winter much more, because their house can get air from outside, even though it's winter, so the house gets much cooler. Because in summer it doesn't trap the heat, so it doesn't trap the heat all year, so they get a bit colder in winter, because the conduction there's no caption of the heat inside the house anymore. That's very nice. Okay. That was very informative and nice, and I had so much fun.
Yeah, thank you very much.
I find it very
It was fun talking to you.
Thank you. And I find it very interesting, honestly, and I'm sure everybody else will. And hopefully we will do this again sometime.
Yeah, so do I.
Yeah.
We have so many other topics in engineering to talk about.
Of course, yeah. I would be glad to do that again.
Yeah.
Thank you.